Hello, these problems, let's see, we have 6 of them all together, will specifically lead you through the homework problems, other than the Einstein relativity one. So when we're simplifying radicals like square root of 8, square root of 8 means what number times itself gives you root 8, and that's not a perfect square, but what we're going to do is try to simplify this by using our perfect squares. So for instance, if we have the square root of 1, square root of 2, square root of 4, square root of 1 equals 1, not square root of 2, oh geez, fellow human being, square root of 4, square root of 4 would equal 2, square root of 9 will equal 3, square root of 16 will equal 4, and note, all of these perfect squares, I know that because 1 squared equals 1, 2 squared equals 4, 3 squared equals 9, and so on. So we can list those all out, and if you need me to go through those with you individually, I certainly can. You can also simply look them up on Google, like perfect squares. So what we're going to do is to break this down, just makes it a little easier to work with algebraically, is we are going to break this up into 2 factors of 8, one of them being a perfect square. And this is how I like doing it. Writing 2 lines there and indicating that I'm breaking 8, which is underneath the radical, that radical symbol or root symbol, breaking it down into 4 and 2, and 8 factors are 1 and 8 and 4 and 2. If I broke it down into 1 and 8, that doesn't help me because the square root of 1 is just a 1, and then you have square root of 8 left over, so it's not helping us. But if I change root 4, I know that's a perfect square, and root 4 turns into 2. This is the mechanics of how I like working with it. I cross off the perfect square above and then write 2 below. The square root of 2 I did nothing with, and then I'm left with 2 root 2. Now to check to see if I'm done, how do we know when we're done? We know when we're done when this doesn't have any perfect square factors. Obviously it has square root of 1, which is a perfect square, but that doesn't help us because square root of 1 equals 1, and it doesn't simplify the root 2 at all. So that's when we know when we're done. When this number inside here, again, is you can't break it down anymore, or it doesn't have a perfect square factor. So now this number 2, we're going to do the same thing, but this one's a little more instructive because if I list out all of my factors of 32, I have 1 and 32, I have 2 and 16, I have 4 and 8. And if you look here, if I break this down into these, I'm going to cancel that one off because 1's not helping us. So let's look at 2 and 16 and 4 and 8 as our factors. First one I'm going to look at is 4 square root of 8, because square root of 4 is the perfect square. Note, I listed the perfect square first. You don't have to do that, but that's the one that's going to turn into the whole number, and we're going to want that out in front. So typically I like it in the practice of listing my perfect square first. And square root of 4 turns into 2 root 8. And then I ask myself, can this be simplified more? Well, square root of 8, we saw that before. That is square root of 4 times 2. So I'm going to leave that 2 out front. I just brought that down. And then the root 8 breaks into square root of 4 times square root of 2. And then this square root of 4 turns into 2. Again, I bring down this 2. So I have 2 times 2 times root 2. And then I have 2 times 2, which is 4, and I get 4 root 2. And now we've gotten back to the point where this root 2 cannot be broken down anymore. It doesn't have a perfect square factor, so our answer is 4 root 2. That's what happens when I use 4 and 8. What happens when I use 2 and 16? So I'm going to bring that down over here. Square root of 16, that's my perfect square, and root 2. I look at square root of 16, I say, what number times itself gives us 16? That would be 4. 4 root 2. Look, we got the same answer in both cases, but this method was much more efficient. The reason it was much more efficient is we found the largest perfect square factor of 32. The factors of 32 that are perfect squares are 4 and 16. But since 16 is the largest of them, that's the one we want to go with. If you find, and I'll write it over here, the largest perfect, R in there, perfect square factor of this number right here, which is called your radicand. I had to think there for a second, sorry. If you find the largest perfect square factor, just like we did here, it will always simplify in one step from here to here. So that's what you're aiming to find. Now, a little more challenging if we have fractions like this. If I look at 25 and 36, it's saying we divide those first, but that can't be divided or reduced, 25 over 36. However, if we distribute the radical to the top and the bottom, we now can make root 25 into 5 and root 36 into 6. Now, can we do that? Is it possible to, quote-unquote, distribute the radical to the top and bottom? Well, let me show that to you over here. Let's say if I have root 16 over 4. One way we could do this is divide the 16 and 4 inside the radical, which would give us 4, because 16 divided by 4 is 4. And then the square root of 4 equals 2. Well, what if I did it this way? Root 16 over root 4. Root 16 on top is 4. Root 4 is 2. 4 divided by 2 is 2. Works in any case. And we know that works, distributing of the radical to the top and bottom works because radicals are actually exponents. And just like we had the section before, something like this, we distribute the exponent to the top and the bottom. We're not going to get into the details of why radicals are exponents, but they are. So this is okay. So coming back over to here, this is permissible to go from here to here, and that's what you're going to do in your homework. Moving down to radical expressions, what happens when we have addition of two radical terms? Well, radicals are like variables. This is like x plus 6y. If I have 1 root 20 or 1x plus 6y or plus 6 root 5, I can't add those. If we're multiplying, then we can, just like x times y gives us the expression xy. But what we can do is look at 20 here and break down 20 into 5 and 4. And again, I'm going to put the 4 in front. Note I could have broke it down into 2 and 10, but neither of those are perfect squares. Root 4 is a perfect square, so that's why I chose that. The 6 root 5 I did nothing with, so I'm going to bring that down. Square root of 4, the 4 cancels to a 2, or simplifies to be a 2. And now if we look at this, now we have like terms. I have 2 root 5s plus 6 root 5. That's the same thing as 2x plus 6x. And we know 2x plus 6x gives us 8x. So something that is just inherent within combining like terms, we add the coefficients, but the variable stays the same. The 2 and the 6 turns to 8, but the x and the x stays x. And that's obvious, I think, for us when we're dealing with variables. But when we're dealing with radicals, we may have the propensity to add the root 5 and the root 5 to give us root 10, which is incorrect. Again, what we're doing is we're adding the coefficients, so 2 plus 6 is 8. Whoops, sorry, here I go. Fallible human being. Let's get rid of that. 2 plus 6 is 8, and then we keep the root 5, just like 2x plus 6x gives us 8x. So that's adding. What happens when we have radicals that we can't reduce the fraction and the denominator is not a perfect square? Well, in this case, we have this process of what's called rationalizing the denominator. Rationalizing the denominator means that we want to have the denominator to be a rational number. Right now, a radical is an irrational number, meaning infinitely repeating decimal. So the way we can do that is multiply it by itself, because root 3 times root 3 gives us a perfect square. That would be root 9, which gives us 3. However, this is an algebraic expression right here. And in order to keep the algebraic expression the same, we don't want to multiply it by anything other than 1. Because when you multiply by 1, 4 times 1, 5 times 1, and so on, it stays the same, 4, 5. And in this case, this will stay the same, but it looks differently. So in order to multiply by 1, our numerator and denominator have to be the same, because root 3 over root 3 equals 1. And now we can multiply in. On the numerator, I have root 7 times root 3. Those we can multiply together, again, because it's multiplication. The radical would go over the top of the two of them. 7 times 3 is 21. Root 3 times root 3 is root 9, which is the same as 3. Now, why do we do that? Because if you think back to like the unit circle, where we have our coordinates, root 2 over root 2, root 3 over 2, and so on, sometimes it's beneficial within mathematics to have the denominator rationalized. And that works the same here with 6. Root 3 you cannot break down, so what we need to do in this case when we have the addition of two terms is multiply by what is called the conjugate. The conjugate is simply, if I have a plus b, the conjugate of that is a minus b. And anytime we do a plus b times a minus b, that's the factored form of difference of two squareds. If I go a times a, I get a squared. A times negative b will be minus ab. B times a, I'm going to write in the order of a times b. I can do that in any order, right? Multiplication is commutative. 2 times 3 is 3 times 2. And then I'm going to multiply b by negative b, which gives us negative b squared. If we cancel these out, that gives us a squared minus b squared. How does that help over here? Coming back over to this right here. So if I go 2 plus root 3 times 2 minus root 3, that's the same thing as a plus b times a minus b. Before we get into that calculation, remember we have to multiply. If this right here is an expression, in order to multiply without changing it, we have to multiply it by 1. So whatever we multiply the bottom by, we also have to multiply the top by. So in the numerator, I have 5. I'm going to distribute it into both of those. I'm going to write my division bar here. I'm going to move this up, give myself some space. So 5 times 2 would give us 10 minus 5 times negative root 3 would give us negative 5 root 3. Remember, we treat that radical like a denominator, like a variable, excuse me. And in the denominator here, we're going to have the same thing that happens over here. These middle terms will cancel. So I don't even have to concern myself with what the middle terms are. I just have to do the first term times the first term. 2 times 2 is the same as a times a, or a squared. 2 times 2 is 4. Minus, right, minus b squared. Minus root 3 times root 3 is just 3. Root 3 times root 3 is the same as root 3 squared, or just 3. And remember, those middle terms cancel, so it will happen the same over here. The middle terms in this case would be 2 root 3 and negative 2 root 3, but adding those together, they cancel. We don't even have to write them. So now if I simplify this, 10 minus 5 root 3, nothing to do in the numerator. But in the denominator, I get 4 minus 3, which equals 1, and we are done. And of course, you could write it as 10 minus 5 root 3. If this is like 2 or 4 or something else, you would just leave it as that. Okay, those problems will help you with all of the problems that you have on your homework.